Hello everyone. So we'll go through the seventh video in the series, that is let's build GPT. At least if I look towards his plan, right, I think we were still in progress with this, and we haven't gone through these yet. I'm not sure he's going to post those or not, but we'll try to find if there are some other courses that teaches this, or any other videos that goes through that, or if we can go through the research paper and just try to understand what's happening there. Okay.
Now, this is just one example.
Believe it or not, data science is the fastest growing field. You'll see plenty of opportunities if
Example of the prompt. People have come up with many examples, and there are entire websites that index interactions with ChatGPT. And so many of them are quite humorous. Explain HTML to me like I'm a dog. Write release notes for Chess2. Write a note about Elon Musk buying a Twitter, and so on. So as an example, please write a breaking news article about a leaf falling from a tree. In a shocking turn of events, a leaf has fallen from a tree in the local park. Witnesses report that the leaf, which was previously attached to a branch of a tree, detached itself and fell to the ground. Very dramatic. So you can see that this is a pretty remarkable system, and it is what we call a language model, because it models the sequence of words or characters or tokens more generally, and it knows how sort of words follow each other in English language. And so from its perspective, what it is doing is it is completing the sequence. So I give it the start of a sequence, and it completes the sequence with the outcome. And so it's a language model in that sense. Now, I would like to focus on the under the hood components of what makes ChatGPT work. So what is the neural network under the hood that models the sequence of these words? And that comes from this paper called Attention is All You Need. In 2017, a landmark paper in AI that produced and proposed the transformer architecture. So GPT is short for Generatively Pretrained Transformer. So transformer is the neural net that actually does all the heavy lifting under the hood. It comes from this paper in 2017. Now, if you read this paper, this reads like a pretty random machine translation paper, and that's because I think the authors didn't fully anticipate the impact that the transformer would have on the field. And this architecture that they produced in the context of machine translation, in their case, actually ended up taking over the rest of AI in the next 5 years after. And so this architecture, with minor changes, was copy-pasted into a huge amount of applications in AI in more recent years. And that includes at the core of ChatGPT. Now, what I'd like to do now is I'd like to build out something like ChatGPT, but we're not going to be able to, of course, reproduce ChatGPT. This is a very serious production grade system. It is trained on a good chunk of internet, and then there's a lot of pre-training and fine-tuning stages to it, and so it's very complicated. What I'd like to focus on is just to train a transformer-based language model. And in our case, it's going to be a character-level language model. I still think that is very educational with respect to how these systems work. So I don't want to train on a chunk of internet. We need a smaller dataset. In this case, I propose that we work with my favorite toy dataset. It's called Tiny Shakespeare. And what it is basically, it's a concatenation of all of the works of Shakespeare, in my understanding. And so this is all of Shakespeare in a single file. This file is about 1 megabyte, and it's just all of Shakespeare. And what we are going to do now is we're going to basically model how these characters follow each other. So for example, given a chunk of these characters, like this, given some context of characters in the past, the transformer neural network will look at the characters that I've highlighted and is going to predict that G is likely to come next in the sequence. And it's going to do that because we're going to train that transformer on Shakespeare. And it's just going to try to produce character sequences that look like this. And in that process, it's going to model all the patterns inside this data. So once we've trained the system, I'd just like to give you a preview. we can generate infinite Shakespeare. And of course, it's a fake thing that looks kind of like Shakespeare. Apologies for, there's some jank that I'm not able to resolve in here, but you can see how this is going character by character, and it's kind of like predicting Shakespeare-like language. So, verily, my lord, the sights have left thee again, the king, coming with my curses with precious pale. And then Tranio says something else, etc. And this is just coming out of the transformer in a very similar manner as it would come out in ChatGPT. In our case, character by character. In ChatGPT, it's coming out on a token by token level, and tokens are these sort of like little subword pieces. So they're not word level, they're kind of like word chunk level. And now I've already written this entire code to train these transformers, and it is in a GitHub repository that you can find, and it's called NanoGPT. So NanoGPT is a repository that you can find on my GitHub, and it's a repository for training transformers on any given text. And what I think is interesting about it, because there's many ways to train transformers, but this is a very simple implementation. So it's just 2 files of 300 lines of code each. One file defines the GPT model, the transformer, and one file trains it on some given text dataset. And here I'm showing that if you train it on an open web text dataset, which is a fairly large dataset of web pages, then I reproduce the performance of GPT-2. So GPT-2 is an early version of OpenAI's GPT from 2017, if I recall correctly. And I've only so far reproduced the smallest 124 million parameter model. But basically, this is just proving that the code base is correctly arranged. And I'm able to load the neural network weights that OpenAI has released later. So you can take a look at the finished code here in NanoGPT. But what I would like to do in this lecture is I would like to basically write this repository from scratch. So we're going to begin with an empty file, and we're going to define a transformer piece by piece. We're going to train it on the tiny Shakespeare dataset, and we'll see how we can then generate infinite Shakespeare. And of course, this can copy paste to any arbitrary text dataset that you like. But my goal really here is to just make you understand and appreciate how under the hood ChatGPT works. And really all that's required is a proficiency in Python and some basic understanding of calculus and statistics. And it would help if you also see my previous videos on the same YouTube channel, in particular my makemore series, where I define smaller and simpler neural network language models. So multi-allelic perceptrons and so on. It really introduces the language modeling framework. And then here in this video, we're going to focus on the transformer neural network itself. Okay, so I created a new Google Colab Jupyter notebook here. And this will allow me to later easily share this code that we're going to develop together with you so you can follow along. So this will be in the video description later.
Trying to find the text. If you're not feed with the fastest way to Prepare.py. Data Shakespeare here. Um, I think I had the code to get it to work in a Windows machine. It was curl hyphen O.
Now, here I've just done some preliminaries. I downloaded the dataset, the Tiny Shakespeare dataset at this URL, and you can see that it's about a 1 megabyte file. Then here I open the input.txt file and just
Okay, let me anyway go through it. Then we'll
read in all the text as a string, and we see that we are working with 1 million characters roughly. And the first 1,000 characters, if we just print them out, are basically what you would expect. This is the first 1,000 characters of the Tiny Shakespeare dataset, roughly up to here. So far so good. Next, we're going to take this text, and the text 1,000, first 1,000, and we see that here I'm working with 1 million characters.
it's same. Before we proceed here, let me speak. All speak first. Here, all resolve rather to die than to famish. Resolve first. You know, Kisses Marcus is chief enemy of people.
Characters roughly. And the first 1,000 characters, if we just do Tiny Shakespeare dataset, this text. And the text is a sequence of characters in
Set means it will take all the unique values in there So these are the characters. Then it is converting it to a list, and then the list becomes like this. And so this is just taking into account all the unique characters that are present there, and um, sorting them out as well. So there are 65, so 26, I think, A to Z, capital, small, 52, and then few special characters and slash and will be coming. Those are the input characters and everything. Nothing to print as such there. We can
Python.
print it.
So when I call the set constructor on it, I'm just going to get the set of all the characters that occur in this text. And then I call list on that to create a list, and then I sort that. The number of them is going to be our vocabulary size, the characters. There's 65 of them in total. There's a space character, and then all kinds of special characters, sort of like possible characters that the model can see or emit. Okay, so next we would like to develop some strategy to tokenize the input text. Now, when people say tokenize, they mean convert the raw text as a string to some sequence of integers according to some according to some vocabulary of possible elements. So as an example, here we are going to be building a character level language model, so we're simply going to be translating individual characters into integers. So let me show you a chunk of code that sort of does that for us. So we're building both the encoder and
So what it does, it assigns a number to each of the character here, as we have seen before as well, right? So for I comma ch, enumerate usually gives us if you can see, right, um it's a slash n, so you see like this, and then one is space, so it is assigning a number to each of this, and it is creating a dictionary out of it, and then we'll do the ulta as well. So it is string to index. It means if I put in here capital A, I will get 1, and the same happens here as well, where it is index to character. So it's in code. Let's see. And S. Oh, okay. So it's like a function, lambda function. S is you can think of it as a string, and then what we'll do is we'll go through each of the character in S and try to get there. Sorry, try to get there index. Okay. And sorry. And this is decode lambda L. When we send it a string of those index L, it is sending me oh, sorry, that is not stoic, it is stoi. It will be I. So you can write it everything. Hi, my name, sorry, hi, my name is Abhishek. Sorry. So it gives you these numbers that I initially showed, right? The numbers assigned to each character. So 20 is small h. So this, right, it has been assigned a 20 number in the index. And then you can do the ult as well. So if you have an encode, then you can call decode as well.
And the decoder. Text, like hi there. So for example, take this list and decode it to get back the exact same string. So it's really just like a translation to integers and back for arbitrary string. And for us, it is done on a character level. Now the way this was achieved is we just iterate over all the characters here to encode some string, reverse mapping, and concatenate all of it. Now this is only one of many possible encodings or many possible sort of tokenizers, and it's a very simple one. But there's many other schemas that people have come up with in practice. So for example, Google uses a sentence piece. So sentence piece will also encode text into integers, but in a different schema and using a different vocabulary. And sentence piece is a subword sort of tokenizer. And what that means is that you're not encoding entire words, but you're not also encoding individual characters. It's a subword unit level. And that's usually what's adopted in practice. For example, also OpenAI has this library called TickToken that uses a byte pair encoding tokenizer. And that's what GPT uses. And you can also just encode words into, like hello world, into a list of integers. So as an example, I'm using the TickToken library here. I'm getting the encoding for GPT-2, or that was used for GPT-2. Instead of just having 65 possible characters or tokens, they have 50,000 tokens. And so when they encode the exact same string, hi there, we only get a list of 3 integers. But those integers are not between 0 and 64. They are between 0 and 50,256. So basically, you can trade off the codebook size and the sequence lengths. So you can have very long sequences of integers with very small vocabularies, or you can have short sequences of integers with very large vocabularies. And so typically people use in practice these subword encodings, but I'd like to keep our tokenizer very simple. So we're using character level tokenizer, and that means that we have very small.
It means if you are tracking at a character level, right? How many characters you will have? 26. Small a to small z. If we take in capital A to capital Z, it will be again 26. So maximum it is coming around 65 or something like that. maximum or whatever you can see in your keyboard, right? That's the character. So that will be small. But if you are trying to encode words or something like that, right, that will be very huge, means in terms of millions and millions of words, so it will be pretty large. So that's what he's saying.
Codebooks. We have very simple encode and decode functions, but we do get very long sequences as a result. But that's the level at which.
And the thing is, because we are giving number to each character, right? So high space there. Every character will have a number representation to it. If it was say word, if you would have done word, one number for HII, one number for space, one number for there. Just taking an example, then it would have been three. But the vocabulary size would be pretty huge because we would have seen so many words coming in there, right? So that's how it is.
Which we're going to stick with this lecture because it's the simplest thing. Okay, so now that we have an encoder and a decoder, effectively a tokenizer, we can tokenize the entire training set of Shakespeare. So here's a chunk of code that does that. And I'm going to
As if we were doing it here, taking like this and encoding it, it's taking the whole of text here and then equal to dot long. Data not d type. So for the first initial 100 characters, right? This is what we get. So this means F is 18, I is 47, and again if I come it will 47. See again I comes here, right? So 0, 1, 2, 3, 4, 5, 6, 7. So in the index 1 and 67 you should see the same number. So 1 is 47, 2, 3, 4, 5, 6, 7. See again you see 47. This is representing small I. So that's the whole representation.
start to use the PyTorch library, and specifically the torch.tensor from the PyTorch library. So we're going to take all of the text in Tiny Shakespeare, encode it, and then wrap it into a torch.tensor to get the data tensor. So here's what the data tensor looks like when I look at just the first 1,000 characters, or the 1,000 elements of it. So we see that we have a massive sequence of the first 1,000 characters here. So I believe, for example, that 0 is a new line character, and maybe 1 is a space. Not 100% sure. But from now on, the entire data set of text is re-represented as it's just stretched out as a single very large sequence of integers. Let me do one more thing before we move on here. I'd like to separate out our data set into a train and a validation split. So in particular, we're going to take the first 90% of the data set and consider that to be the training data for the transformer. And we're going to withhold the last 10% at the end of it to be the validation data. And this will help us understand to what extent our model is overfitting. So we're going to basically hide and keep the validation data on the side because we don't want just a perfect memorization of this exact Shakespeare. We want a neural network that sort of creates Shakespeare-like text. And so it should be fairly likely for it to produce the actual, like, stowed away true Shakespeare text. And so we're going to use this to get a sense of the overfitting. Okay, so now we would like to start plugging these text sequences or integer sequences into the transformer so that it can train and learn those patterns. Now, the important
The only thing that I want to check is okay, using the probability distribution, right? We used to pick one element. Yeah, sorry.
thing to realize is we're never going to actually feed the entire text into the transformer all at once. That would be computationally very expensive and prohibitive. So when we actually train a transformer on a lot of these datasets, we only work with chunks of the dataset. And when we train the transformer, we basically sample random little chunks out of the training set and train on just chunks at a time. And these chunks have basically some kind of a length and some maximum length. Now, the maximum length typically, at least in the code I usually write, is called block size. You can find it under different names like context length or something like that. Let's start with the block size of just 8. And let me look at the first train data characters, the first block size +1 characters. I'll explain why +1 in a second. So this is the first 9 characters in the sequence, in the training set. Now what I'd like to point out is that when you sample a chunk of data like this, so say these 9 characters out of the training set, this actually has multiple examples packed into it. And that's because all of these characters follow each other. And so what this thing is going to say when we plug it into a transformer is we're going to actually simultaneously train it to make a prediction at every one of these positions. Now, in a chunk of 9 characters, there's actually 8 individual examples packed in there. So there's the example that when in the context of 18, 47 likely comes next. In the context of 18 and 47, 56 comes next. In the context of 18, 47, 56, 57 can come next, and so on. So that's the 8 individual examples. Let me actually spell it out with code.
So what he's saying, they means that 18 character that initially that we have, right? We are not predicting. It is saying that we are always talking in terms of the context. So 47 coming in context of 87, then 56 coming in context of 1847. So like that we are going. I think that's what I could get
1840
from.
in a individual. Now, in a chunk of 9 characters, there's actually 8 individual examples packed in there. So there's the example that when in the context of 18, 47 likely comes next.
Yeah. So there is no context for 18, so that's why it is just 8 examples that are there.
In a context of 6 examples. Let me actually spell it out with code. So here's a chunk of code to illustrate. X are the inputs to the transformer. It will just be the first block size characters. Y will be the next block size characters. So it's offset by 1. And that's because Y are the targets for each position in the input.
Okay.
And then here I'm iterating over all the block size of 8. And the context is always all the characters in X up to T and including T. And the target is always the Tth.
Mm. So what it is saying is um if it's an so initially it is going 0 to block size is taking it. Okay. Oh wait, but it has to move, right? Yeah. So what it is saying is, if I see H coming in there, if the block is fixed, say let's take this as an example. Okay, so what he's saying is, for each block size, so x equal to temp underscore data, just so that we don't need to work with numbers. I can make you understand what's happening. Underscore size equal to 8. Okay, so it takes here 8, and then it's first 8 characters, and then 1 block size. Context equal to, it is taking target equal to, when input is context and the target. So see, so x, he is taking 0 to 8, so 8 characters, so it starts my like till that it goes, that's the block size. So x is till here, y is 1, so from here it starts and it goes to m. Okay, what it is saying is, if I see an h, okay, uh, if I see an h, okay, my target will be I, means in the context of h I see I, then the next word, when I see I should predict a space. When I see hi and m, I should predict y. When I get hi my, I should get oh, again it's a space. So it is trying to create examples out of it. So for whole text, right, we'll go this way and create all the set of examples, which will comprise of the context and the target that we want to achieve, and we will store that, and then we'll train our neural net. So if it sees this in the input, this is the target that is expected. Okay.
Character, but in the targets array y. So let me just run this. And basically it spells out what I said in words. These are the 8 examples hidden in a chunk of 9 characters that we sampled from the training.
So it's just giving it a number. H is 18. No, sorry, it's so different. So it is fi. This is the first how it is going through. So fi if I see. So what I showed here in terms of characters, it is coming in terms of the numbers.
Set. I want to mention one more thing. We train on all the 8 examples here with context between 1 all the way up to context of the block size. And we train on that not just for computational reasons because we happen to have the sequence already or something like that. It's not just done for efficiency. It's also done to make the transformer network be used to seeing contexts all the way from as little as 1 all the way to block size. And we'd like the transformer to be used to seeing everything in between. And that's going to be useful later during inference because while we're sampling, we can start a sampling generation with as little as 1 character of context. And the transformer knows how to predict the next character with all the way up to just context of 1.
Okay.
And so then it can predict everything up to block size. And after block size, we have to start truncating because the transformer will never receive more than block size inputs when it's predicting the next character. Okay, so we've looked at the time dimension of the tensors that are going to be feeding into the transformer. There's one more.
If I give 9 characters, yeah, it will take the last 8 characters and try to predict the next token. So that's how it will work. Okay. So if I give it high my nm, that is 9 characters, it will make prediction based on this itself. It will try to truncate then and try to predict E here.
More dimension to care about, and that is the batch dimension. And so as we're sampling these chunks of text, we're going to be actually, every time we're going to feed them into a transformer, we're going to have many batches of multiple chunks of text that are all like stacked up in a single tensor. And that's just done for efficiency, just so that we can keep the GPUs busy, because they are very good at parallel processing of data. And so we just want to process multiple chunks all at the same time. But those chunks are processed completely independently, they don't talk to each other, and so on. So let me basically just generalize this and introduce a batch dimension. Here's a chunk of code. Let me just run it, and then I'm going to explain what it does. So here, because we're going to start sampling random locations in the dataset to pull chunks from, I am setting the seed so that
This is just random. We can get specify that we both get this. Let's explain what's happening. Something this let's take this this is one. That is about. So she's teaching. So what we'll be saying is the length of this is so it subtracts 8 from 22 so that the last law of 8 that's it. So if we give it till say here we don't have 8 characters after the after. So we are making sure if we are making a prediction, the last it can predict it till here so that we can take 8 characters from that. The intention of this is to pluck out 8 character size chunk from that 10 data. So max the last that 8 character that we can do is this itself. That is the 8 character. That is addition. Okay, so the index of this, right? Whatever the index of this will be. So this is 14th index, is whatever you see, right? Till that we will try to get a number. We can't say 15 because after 15 we don't have 8 characters. Then after 14 then we will 8 characters will be this much. And so what it is saying is backside. So we are generating random indexes, okay, of 22 minus 8, that is 40, means from 0 to 40 we try to predict one number and how many of them. So this is the way to specify the array size that you want. So here it is 4 cross 2. If we specify it here to write, say it becomes 4 cross 2. So from between 0 to 14, right, it is trying to predict 8 numbers. So 0 to 40, we're trying to predict index number. Now when we have predicted the index number, right, on that points, let's do it inside of so it predicted 4 numbers because that's how it works. Now we have made those are the index set. Now from there on, right, we will see 8 characters how we lost in there. So that's what this is. Index for each of those index, say 11. We'll look at 11 and then 11 plus 8, that is 19. From 11 to we will look at 19 characters. That is 8 characters. And we will do that for each of this and we will stack them on up. Our name is becoming because mostly Pascal will work with string. So initially, as I told, right, we randomly selected 4 numbers, 0736, which corresponds to HAM. And now for each of those index that we calculated from this end, we are taking 8 characters from that. This is, say, first was 0. So 0 is connected to 8 characters we are going to calculate. That is 0 to 8 from there. Okay, and you see the number representing that. The next we got is with these 20 corresponds to LH 47 to small I, 1 which stays 51 to M. It's 20, 47, 1, 51, 60, 24, 60. So first 8 there. Then we will do 70. So from there, then we are trying to get 8 to the 79 is A, and 51 is small m, 43 is that we are getting 8, 8. So this is just the starting point from where we should look for each of 8 characters and we are storing. Next, what we are doing is we are stacking y as corresponding to how the target should be. So this is just offsetting by 1. So 20, 47 we store. Here we are storing from 47. 1 given the radius of 39 and 1 more character. The reason is later what we will do something like this. Okay? So if we see so in the context of 20, we will get 47. In the context of 2047, we should get 1. In the context of 2047, 1, we should get 1. In the context of like that, like that, like that. So if we see these many characters as well, we should see 50. That's why you see the 1 letter after 1 letter after the extra. So that's one, and that's where this comes into the picture. So that so it's just so these are the 4 that we so this itself is a complete example, and so many examples are embedded in this itself. So what we also be talking about the first batch. This is the first batch. So we 0 by 0. What we will take is in again, then we are going block size by block size. So this is what we are doing. One. So initially that will be 0 plus 1, that is 1. So we will take 47. And what we should see the other side of it. Y in the context of 47, we should see 57. the context of 4757, that is 0 to 2, we should see 1. This can be right? So the node out of this, the model happens if I see 51, that is 0 with 1, that is 51. In the context of that, we should get 43. And in the context of 0 to 2, that is t and 0 to 2, we should see 0, 2. So 0 to 2, we should see 2, that is 1. 0 to 3, which 3 is always excluded. So it is, if it is written 0 to 2, right, it becomes 0 and 1. If it is written 0 to 3, it becomes 0, 1, 2. If it is written 0, 4, it is 0, 1, 2, 3. Plus 51, we should and so these, to form just one batch, right? These are the number of design. The next batch, these are like that. Third batch, these are like that. The fourth batch, these are like that. That is in function. So this is what this here. That will happen from the whole district. So first we'll split the main variable and pass it on. Split the thing. Too much. We are dividing, then we are calling this individual and then we are saving it as split.
That in the random number generator, so that the numbers I see here are going to be the same numbers you see later if you try to reproduce this. Now the batch size here is how many independent sequences we are processing every forward-backward pass of the transformer. The block size, as I explained, is the maximum context length to make those predictions. So let's say batch size 4, block size 8, and then here's how we get batch for any arbitrary split. If the split is a training split, then we're going to look at train data. Otherwise, then I actually generate batch size number of going to my in a 4x8 tensor. So here's what I'm printing then. When I sample a batch XB and YB, the inputs to the transformer now are rows Y functions. The transformer input, the target is 5, etc. Or like when it is a 52, 58, 1, the target is 58. Examples packed in to a single batch of the input X, and then the desired targets are in Y. And so now this
Sorry, just sorry, I was just telling that he's getting the same example 24, 43, 24, 43, 58. Similar. Why? Because we have both fixed the seed as string.
integer tensor sends into neural networks. Now we're going to start off with the simplest possible neural network, which in the case of language modeling, in my opinion, is the bigram language model. And we've covered the bigram language model in my makemore series in a lot of depth. And so here I'm going to sort of go faster, and let's just implement the PyTorch module directly that implements the bigram